Welcome to video 14 in a series of introductory videos for the InventorCAM CNC programming software. This video's topic is HSM. The HSM toolpath is a target-based finishing or semi-finishing toolpath, and it is a very good companion to any of the 3D-based roughing toolpaths in InventorCAM. This is actually a really good combination with HSR that you saw in video 13. A lot of the setup for the HSM toolpath is very similar to HSR, the one you see in video 13. So I would refer you to video 13 for the actual setup of these parts. In this video, I'm going to go through each option of HSM simply because there's many of them here. So we'll start with the first one here. So horizontal machining is the first on the list, but you'll see that there's an expanded list here of many different options for the HSM. And really, all you're doing with each of those options is finding a toolpath that best fits the geometry you'd like to machine. The geometry itself is the target. So the solid that you chose when you first defined your InventorCAM part. That being said, you can use the constraint boundaries to limit the travel of the tool. So that the constraint boundary with the machining options allows you to make a really good finishing toolpath for different areas of your part. And for this video, I've actually just used the automatically selected boundary of the entire part. Now, what we'll see here is how the different options apply to the overall part. We can also get an idea as to how they may not fit certain areas. Again, the geometry that you choose is just the target. You use the constraint boundaries to limit the travel of the tool, and you choose the technology options up here to use the best tool path for the selection of the geometry with the boundary area. In this case, we choose the tool. Now with HSM, you can use any type of finishing tool you want. You can use a ball nose or a bull nose. We'll go straight to passes. Passes is where you'll see the specific parameters of each of these machining technologies. In this case, we're doing horizontal machining. If you take a look at the bottom corner there, bottom left corner, you'll see that horizontal machining only applies to horizontal faces, anything at 0 degrees to the XY plane. We're doing finishing, so on the wall offset and the floor offset, I'm leaving 0. The minimum offset of this Stepover on horizontal areas is just going to be 95 thou. I'm smoothing out the toolpath, so I'm eliminating any small linear movements and just creating an arc movement for each one, and that's actually going to be controlled by the smoothing tab. So there's my max radius, and those are my offsets, my tolerances. Detect core areas will detect any kind of large area that could be considered a core, and it'll actually just approach the toolpath from the outside going in. My envelope here, my Z top, Z bottom, essentially just how much of the target I'd like to machine. So I've just chose the top of the part and the bottom of the part. We're going to try and finish the whole thing. Under link, we have the same controls you would have seen in video 13. Essentially just climb milling, conventional milling, bidirectional. If we'd like to link it by Z levels or by cluster, cluster meaning selections of areas. This is a more advanced option that you can try out, but essentially all you're really doing is just choosing different selections and then machining those areas before you move on. Everything else is the same as video 13. Our ramping, our strategy, our retracts, again, just higher level controls over this toolpath. You'll notice that with each one of these technologies that we present here, it's really the passes area where you see the main difference. So if I exit out of here and we'll take a look at the calculated toolpath, only the horizontal areas of this part have been machined. The flip side of that is the constant Z machining. So this will be anything that is tapered, curved, anything that is not completely flat. Under passes, you'll see we have the same sort of control here. So 0 on the walls and the floor. We only have a step down. We still have the smoothing. Our Z top, Z bottom is the same. And we can limit the travel of the tool by the angles. Once again, this is for any kind of non-horizontal area. So we can actually limit the travel on any one of those angles from the vertical. So basically from 0 to 90, I could control this even further by saying only areas that are at 90 degrees to 30 degrees, something like that. Again, because we're talking about movement in the Z direction, I'm going to automatically add any passes that need to be done for any feature that falls in between that 10 thou step. Again, exit out of there, take a look at that toolpath, and it avoided all the horizontal areas, and it's only done the tapered and the curved areas. Linear machining is one of the technologies that you'll see under HSM that is very similar to the way that we did the HSS toolpath that you would have seen in videos 12 and 13. Linear is essentially, again, we're just going to choose a direction. In this case, either an angle from the x-axis. In this case, I've done 90 degrees to the x-axis. So we're going to zigzag this way across the part. I've got a step down and a step over. I'm leaving 0 on the walls and the floor. Same Z top, Z bottom. And again, because we're talking about a toolpath that could handle tapers and curves, I've got angles as well. So I can limit the travel in that respect as well. If I exit out of here, we'll take a look at that toolpath, and you can see that it's zigzagging back and forth. Now, I've done this for the entire part. This gives us a good example of why you may want to use the constraint boundaries to limit the travel of the tool. In some areas, this linear toolpath looks great. But if we zoom in on one of these bosses here, you'll see that because I've done a certain amount of step over, I've actually stepped along this taper by that much right there. And that's not going to leave the best finish. So again, that's why I mentioned that a lot of the technologies that you'll see from HSM, they should be applied using a constraint boundary. That way you can get a good finish in a particular area. In this case, I probably would have limited the travel of the linear to only these areas maybe up here and these surfaces here. That gives us a nice little linear finish along that surface. And any one of these areas right here, I probably would switch to a completely different strategy. If we take a look at the radial machining, I've done a constraint boundary that limits the travel to only that dish area. So only the areas within that contour are going to be finished, going to be machined. I'm still leaving 0 on the walls and the floor. I've defined the center of my radial pass to be the center of that dish, and I've given it some angle limits as well. So you see that I have a minimum radius and a maximum radius, and I'm going to do a full 360 radial. So if you take a look at the bottom left corner, essentially radial is just almost like a star pattern. It goes from that center, and it just zigzags back and forth with a 20,000 step over at the end of each fan, and it generates a toolpath that essentially looks like that. So if we zoom in there, only the surface that fell inside of my constraint boundary is being machined, and it's zigzagging back and forth from center to the outermost radius. The next one is spiral. So if we take a look at the passes section, we'll see similar controls. In this case, though, spiral is going to lay a spiral toolpath on whatever surface I choose. In this case, though, again, I've limited the travel of the tool to only within that dish. I've included the center as well, just to show you how the spiral benefits on this sort of shape. 0 on the walls and the floor. The center is a similar center. We're doing a 20,000 step over radially in the spiral. We're going to go from 0 radius to the radius of essentially the dish itself. So if we take a look at that toolpath, we'll see that we start at the center, and we're just spiraling out, and we're laying down a spiral toolpath on the part. If we take a look at that from the top view, it looks like a complete spiral. Again, you choose the strategy that best fits the geometry. So between radial and spiral, you've got all your kind of turned parts, any kind of cones, any kind of circular repeating kind of parts covered. Next in the series is again something similar to what you would have seen in video 12 and 13 from HSS. In HSM, we have a morphed machining toolpath. If we take a look, we still have the constraint boundaries. So in this case, if we zoom out, we can see that the constraint boundaries is the outer edges of that surface right there. So I intend to just machine whatever's inside that surface. We have an additional section in morphed machining called drive boundaries. And this is why I say this is similar to what you would have seen previously in the HSS toolpath. We're choosing a start curve and an end curve. And we're going to morph a toolpath on that surface within that constraint boundary that morphs between the start curve and the end curve. Under passes, we have just a few parameters here that we're going to use to control this. We're just going to do a 20,000 step over from the start curve to the end curve, leaving 0 on the walls and the floor, and we're going to cover the full 90-degree spread. If I check that box there, we'll see that we've morphed the toolpath that starts off on that direction, and as it gets closer to the other side, gradually will take the shape of that final curve. Now, offset cutting again, is very similar to some of the other toolpaths you would have seen. Specifically here, it's somewhat like a profile toolpath, where you're using something like a clear offset. Here, we're actually going to drape the clear offset toolpath over this over the part. I'm going to use the automatically defined constraint boundary, but under my drive boundary, I'm choosing just that edge right there. If we go to passes, you'll see that I've added a clear offset of 300 thou. 0 on the walls and the floor, full 90-degree spread, the same envelopes, with a step over of 30 thou. If we take a look at that, it is simply just a clear offset. I've told it to lay a clear offset toolpath on the target within that boundary area and just basically clear offset from that edge there that I've selected. So again, it's a very simple toolpath. It has its use here because I just wanted to machine just that particular area. As with any other 3D toolpath or some basic toolpaths like Profile or Pocket, we have a rest option. Constraint boundaries, again, is for the overall part. The additional function here is the reference tool. So I'm basically telling it what the previous tool size was. So the previous tool was my 1/4 inch tool. Here I'm using a 1/8 tool. And we have what is sort of similar to a pencil milling toolpath, which we'll get to later in this video. I'm just giving it a bitangency angle. So you'll see from the bottom left corner, any angle that is made by the contact points of the ball nose tool creates a bitangency angle. This is how InventorCAM is going to know if that is a tight enough curve that the previous tool could not get in. My step down here is going to be 20 thou, and my step over is going to be 20 thou. Same work envelope in terms of Z top, Z bottom. If we take a look at that, it's essentially just a roughing toolpath. It realized that the previous tool could not get into those areas. So some additional work was done near these bosses here, and all the tight corners, tight radii that were done. 3D constant step over is one of the more powerful strategies inside the HSM toolpath. Essentially what it does is, using the constraint area, I'm just going to tell it to stay within that circle right there. And I'm going to step over from, again, the same circle. Passes, this is a step over from those contours that I selected under drive boundaries. So we're just going to do a horizontal and vertical step over of 20 thou from that geometry. So if I check that box there, you'll see again that it basically offset from that circle by the 20 thou in the vertical and the horizontal, and it drapes the toolpath. If I had set that to the overall part, the overall constraint boundary, I would have had a constraint boundary that basically does the same thing, offsets from that contour and does the whole thing. Pencil milling is what we saw similar in the rest milling option, but here it's going to do it for the overall part. So essentially, again, we're defining a bitangency angle for whatever size tool we want, and it's only going to machine in the areas that are small enough, tight enough, that meet this bitangency angle. So if I check that box there, it's really just the tight areas. It just does one pass. Now that is just pencil milling. It lays down that one path there. If I had switched this to parallel pencil milling, we'll get the option of a step over and a step down from there. And we can limit the number of cuts as well. So what that would actually look like is, if we calculate that, we should get more than just the one pass. We should get some additional passes there. So there's our limited of 5 cuts, and we just kind of paralleled to that toolpath. So we can actually machine a little deeper with more cuts into that corner. 3D corner offset, again, you're going to give it a constraint boundary, and it's going to use the same sort of parallel pencil options to define bitangency angles. That way we can see the tight areas, and then offset from there. So it's actually, you can see that there's many start points where it does the offset and just spirals out. Again, this is one of the more powerful toolpaths where you can kind of just generate a toolpath that overall will machine a somewhat nice surface. You can kind of see that in some areas, it actually accounts for the fact that there's some taper there, some curvature there. Again, this is one where you could probably apply it to the whole part, but overall, the theme of HSM is whatever toolpath you want to generate, it's usually going to use a constraint boundary and the strategy to best fit the geometry. So if it's curved geometry or circular geometry, you're going to use things like spiral, maybe offset contour, that sort of thing. It essentially is whatever you need in terms of a finish. Any questions on this or anything else that you see in the series of videos, you can always call us at 1-866-975-1115, extension 2. You can send us your parts and your questions via the ticket system at solidcamsupport.com, or stay tuned for the rest of the videos in this series of videos and on the YouTube channel. Thanks for watching.